Welcome back. I'm Ashwin Rao, adjunct professor in ICME, focusing on the intersection of finance and reinforcement learning. I also lead AI at Target, where I hope all of you shop. Let me start by providing a bit of perspective on society-centered computational math. For the past several decades, mathematicians and engineers have developed useful technologies for society. Technologies that make it easy for us to interact with each other, to travel from one place to another, to earn our livelihoods, and to enjoy our community life. As computational mathematics has become more and more sophisticated, we've been able to provide valuable products and services with great conveniences and efficiencies at affordable prices. So one would think we are becoming happier as a society, but we are actually finding that these conveniences and efficiencies are not quite translating to personal satisfaction or societal harmony. There is now a greater need than ever to target our work in computational math to the heart of what society is all about, less about conveniences and financials, and more about being in harmony with the people and environment around us. Here in ICME, many of us think about this a lot when we start working on our mathematical models and algorithms. We ask ourselves if the solution to this problem would be appropriate for society. And more importantly, if there are some details in our algorithm that could lead to undesirable outcomes. When you receive a recommendation to buy something or to connect with someone, I'm sure many of you have wondered if the algorithm knows something about you that you wouldn't want it to know. I'm sure many of you don't like it when an algorithm seems to have stereotyped you in a manner you're not comfortable with. We have to improve our algorithms to overcome biases, to infer with certain types of sensitive data, without certain types of sensitive data, and to be robust to noisy or incomplete data, and to permit fair participation to people of all backgrounds. As researchers in applied math, we obviously don't have the solutions to all of these complex societal issues, but we're eager to do our bit for society with appropriate methods from computational math. As a simple example, think about algorithms that encourage improved behaviors towards each other. More generally, think about algorithms that will provide conveniences and efficiencies without sacrificing privacy or safety. In ICME, we perform a wide variety of research in this space. So today, it's my pleasure to moderate this session where we will share a sample of research topics pertaining to society-centered computational math, presented by a panel of 3 of our esteemed faculty. So now it's my pleasure to introduce our first speaker, Susan Athey. Susan is the Economics of Technology professor at Stanford Graduate School of Business. She's an elected member of the National Academy of Science and is the recipient of the prestigious John Bates Clark Medal, which is awarded to the economist under 40 who has made the greatest contributions to thought and knowledge. Her current research focuses on the economics of digitization, marketplace design, and the intersection of econometrics and machine learning. Today, Susan will share her exciting work on machine learning for targeted treatment assignment. Over to you, Susan.
Thanks so much. Thanks for the kind introduction. And I'm really delighted to be here today. Today, I'm going to be talking about a couple of projects that I've been doing with my lab, which is called the Goal of Capital Social Impact Lab. And in my lab, I give students from ICME the opportunity to work on methods and also collaborate with students from other departments around the university, ranging from the business school to economics to the education school, to be able to put methods to use in collaboration and partnership with social impact organizations. And sometimes, as I'll show today, in collaboration with large for-profit organizations, but making use of their ability to reach users for social impact. We work on a variety of methods, some of which alluded to in Ashwin's introduction. We work a lot on targeting and personalization, trying to do causal inference and build recommendation systems. We help organizations think about how to develop short-term metrics that map into longer-term impacts, which for-profit firms, it's trying to figure out how clicks relate to profits. And for social impact firms, how time spent in an educational app relates to eventual educational attainment that's going to benefit students' lives. We do a lot of work planning and designing experiments and optimizing the design of those experiments for maximal learning, including things like staggered rollouts, also adaptive experiments and bandits, algorithms, et cetera. So, but all of our methods research is really embedded and inspired by problems faced by our partner organizations. So I wanted to talk about today one of those collaborations, and it's a long-term collaboration with PayPal. And here, we have a series of projects with them. Here, I want to focus in on a project around giving at checkout. And so our research questions were, what kinds of appeals to donors increase the quantity of micro giving? And particularly, can appeals based on the impact of a charitable organization work in terms of getting more donations? And that's important because if being impactful helps a charity raise money, that also motivates them to be more efficient and to demonstrate their impact and measure themselves, so it can have an outsized impact. And we also particularly wanted to understand if targeting is important, if different customers would respond to different scripts. So, and again, this is a sort of a series of analyses. So I'm just focusing in on one of them. Here, what we were doing over the last year, and you may have seen these yourself when you checked out over the last year. That was our experiments. If you saw this, if you were checking out from some other type of e-commerce experience, you might have been asked whether you wanted to donate $1 to support a charity. And so what we were experimenting with were the messages associated with that. Now, we had limited space because you can't distract people from checking out. But we randomized the different messages that were seen. And some of them were around the activity of the charity, just explaining what they were. Some of them were around saying what the cost per outcome was. What does $1 achieve? How many people does it feed would be an example of that type of statement. Then we also looked at adding in additional validation from a charity rating nonprofit to say, was it rated 5 out of 5 stars from this charity? Or combining activity information with the cost per outcome. And so we looked at a couple of different charities. This was this is one of our first experiments. So we only did it with a couple of target charities. And what we saw was that there were statistically significant differences. We had a couple 100,000 people per treatment arm. So we were able to tell the differences between these different treatment arms. And we saw that providing relative to a control arm where you just had the name of the charity, providing the cost per outcome gave 4 times as many donations. And then the close runner-ups were things that added information to cost per outcome, like adding validation information or adding star rating information to the information about the cost per outcome. But what we saw was that, and this was robust across each of the charities, that adding additional information to the cost per outcome actually made things worse. So the sweet spot was an intermediate amount of information, but that's something that was concrete. The activity was substantially worse. Just saying what the charity did without any impact information was substantially worse than the cost per outcome information. But then within things that had activity, adding star ratings to the activity, again, actually made things worse. So kind of cluttering up the message in this kind of impulsive environment actually hurt user engagement. So then we made use of a variety of methods that our lab has been developing about estimating and evaluating targeted treatment assignment policies. Now, in this particular application, we didn't see as much benefit to targeting as we might in other settings. One thing is that the messages were all pretty generic, and the charities we by design, we chose sort of generally appealing charities for the first experiment, trying to just make sure we understood what works. But even in this environment where it's not like these are polarized charities or charities that would be related to political issues or anything like that, we did find some benefits to targeting. And so in particular, we found that there were subgroups of people who did, in fact, like the additional information. So we targeted people into two groups on the basis of characteristics, and we found that that there was a smaller group that were adding this validation information, improved outcomes. And so we see for the groups that were assigned to the cost per outcome, they had slightly higher donation rates, with the validation with stars. We then tried to build some insight about what was driving that. And we looked and saw that actually people who were previously donors seemed to like the additional information. Also, we had more women in the group that liked the additional information. So it seems like people who were engaged donors were the ones that were useful to target with this additional validation information. So this is ongoing, and we're doing additional adaptive experiments and bringing additional methods to bear. But this is just a little bit of a taste of the kinds of ways we can bring together experimentation, machine learning methods for social impact. Thank you. And back over to you, Ashwin.
Susan, that was a fascinating presentation. I know you need to leave for another engagement. Thank you for your time here today, Susan. Our next speaker is Ashish Goel, Professor of Management Science and Engineering, and by courtesy, Computer Science. Ashish received his PhD in Computer Science from Stanford. Ashish's research is in design, analysis, and applications of algorithms. Today, Ashish will share his exciting work on market-based algorithms for efficient cryptocurrency transactions. Over to you, Ashish.
Thanks a lot, Ashwin, and thanks to ICME for inviting me. I'm going to focus on one narrow aspect of the agenda of the title that Ashwin mentioned, and that's going to be scaling on-chain asset exchanges via Arrow-Debreu exchange markets. And so just to give you some context of what this means, so what's an asset exchange? So an asset exchange is something where you might come in with some goods or assets that you want to trade, and you might want to make an offer about what you want in return. Okay? So for example, Octopus might say, I want to trade $1 for €1, and then everybody else has their own favorite asset that they want to sell for something that they want to buy. But in fact, Penguin and Octopus get exactly matched, and so they can trade with each other. And the example that you see here is very much like bartering, where Octopus and Penguin are directly talking to each other. But you can also imagine a system where this happens via long cycles. Octopus is something that Snake wants, who is something that Cat wants, and then Cat is something that Penguin wants. And ultimately, you might be able to close the loop. And so when we say an asset exchange, we mean something where people should be able to trade even if there's no direct path between what they exactly want to trade. What does it mean for something to be on-chain? It means that you're doing this on a blockchain. Okay, so these kinds of asset exchanges don't actually exist even without the blockchain. But the reason they've become, the reason we can sort of still exchange things is because there's reserve currency and there are things like the stock market. In the blockchain world and the cryptocurrency world, where you want to do this on chain, you don't actually want a reserve currency. You want to be able to exchange anything for anything else. And if you do something on chain, then if there are many acceptable ways to match buyers with sellers. So for example, in this case, you can match Octopus to Cat and Fish to Penguin, or the other way around. Then you have to do it in a replicable fashion. Okay? So for example, given the same input, you must always get the same output. If it turns out that given the same input, you could potentially get two different outputs, then this is not something that's suitable for a blockchain or an on-chain implementation, because the way blockchains work is that different nodes would, different compute nodes would do their own calculation, and they have to be able to come to consensus that they will indeed produce the correct outcome. So if they're not replicable, you'll never be able to get consensus, and hence an exchange that does not produce replicable results is not suitable for a blockchain implementation. And once again, we are primarily interested in this topic because of the proliferation of cryptocurrencies and the need to exchange them for each other. So we would like to scale them, right? And so existing on-chain exchanges or automated market makers, for example, Unisop, if you have heard of that, achieve replicable operations by serializing transaction processing. So every transaction, I want to sell a Bitcoin for an Ethereum, would happen in serial. You would first sell a Bitcoin for an Ethereum, you would adjust your prices, you would adjust the ledger to see who has how much money left of each type, and then you would do the next transaction. Now, first of all, this means the transaction rates are inherently limited by CPU speed, but also means that you essentially have to be able to exchange things just pairwise, and you can't actually have long cycles by which something is cleared. So the question is, can we parallelize transaction processing replicably? And also, on the economic side, do we have to have pairwise exchanges, or can we do exchanges along cycles? So we would achieve this via this very beautiful model called the Arrow-Debreu exchange market. In this market, imagine you have M agents and they're trading an assets. Each agent starts with an endowment. For example, Optimus might have $3 and €2, or like a Bitcoin and 17 stellars. And then the market produces a public set of prices. Okay? And this public set of prices is denominated in some monopoly money. Let's call them monopols. So the market might say $1 gives you 1 monopole, a euro gives you 2 monopoles. Agents sell their endowment for these monopoles at the given prices. So Octopus would get 7 monopoles. And then agents spend their monopoles to buy whatever set of goods they desire the most. So Octopus might say, well, I'll use my 7 monopoles to buy $5 and a euro, because that makes me happier than having $3 and 2 euros. And so each agent essentially has a utility function which they maximize subject to a budget constraint, and the budget constraint is the number of monopoles that they've received. Okay. Now, of course, for this to work out, you must not oversell or undersell any assets. And a beautiful theorem, classical theorem in economics, is that a set of prices, so that the equilibrium prices also always exist. So what that means is you'll always be able to find a set of prices called an equilibrium of the Arrow-Debreu exchange market, such that after all agents buy and sell assets at these prices, no assets are overbought or oversold. Okay? And these prices exist and can be found in polynomial time for sell offers. So now we have our broad strategy for scaling these asset exchanges via these Arrow-Debreu markets. Suppose we have a fast equilibrium price oracle. Then after price computation, because of these prices, transactions can be processed in parallel while producing replicable results. Right? Octopus right away knows, can I sell a euro for $2? If the prices in the monopoles are such that you can, then yes, otherwise no. Okay? And all of those decisions can be made in parallel, with the assurance that once they are all made, there'll be no shortage or access of any asset. Yeah. And so, because these transactions can be processed in parallel after price computation, we get replicable results. The market becomes more transparent because these prices exist in this phantom currency called monopoles. There's no arbitrage in the system, and you have better liquidity. There's no arbitrage. The existence of prices essentially guarantees no arbitrage. And better liquidity, you can show that there's no arbitrage-free system which will actually trade more assets than the Arrow-Debreu exchange market. Since the market clears, no monopoles are left behind, so there's no actual need for reserve currency. Now, of course, all of this is contingent on being able to find a fast equilibrium oracle. And so imagine there are M sell offers trading and assets. The existing algorithms all run in time polynomial in the market size, which means polynomial in M, where M is the number of sell offers. However, there are far more people in the world than types of assets. So for example, Coinbase has around 4,000 assets, but there are like billions of people in the world. And generally you have around 20 to 100 assets, but you might have up to 1 million offers. So we'd like to have something which is polynomial in N, the number of assets, but not polynomial in M, the number of offers. Okay? And that's basically what we get. We have an algorithm that actually achieves a logarithmic dependence on M and a polynomial dependence on N. We also now have a prototype system that incorporates algorithmic insights that gives sub-second latency for computation of equilibrium prices for up to 1 million orders. It's robust in cases where the price computation does not converge to an optimum solution, and it achieves less than 5 seconds latency for processing an entire block of orders. And we also show that incorporating both buy and sell offers makes the price comparison intractable. So it's important to have just sell offers. This system is a prototype system. It actually exists. If anyone wants to play around with it, let us know. And I forgot to acknowledge my co-authors. I'm going to do that, leave the slide here. This is joint work with my student, Jeff Ramsey, and my CS colleague, David Mazias. Thank you.
Thank you, Ashish, for sharing this exciting area of research. A reminder for the audience that if you have questions for Ashish, please post them on the Expo Slack channel, and Ashish will answer the questions at the end of the session. Our next speaker is Johan Gander, Assistant Professor of Management Science and Engineering. Johan's research develops algorithmic and statistical frameworks for analyzing social networks, social systems, and other large-scale data-rich contexts. He's particularly interested in the challenges of causal inference and experimentation in these complex domains. His work typically falls at the intersection of graph theory, statistics, optimization, and algorithm design. Today, Johan will share his research on evaluating network interventions. Over to you, Johan.
Thank you, Ashwin. And thank you to ICME for the invitation to speak here. Just as Ashish just acknowledged, I also want to make sure I acknowledge this work that I'm going to be talking about was led by Alex Chin, who is a former PhD student who's now at Lyft Research Labs, or Rideshare Labs, I think they're called, and then worked together with Dean Eccles, who's a colleague at MIT. So the problem that this talk is motivated by is the problem of when there's a range of contexts where researchers go into networks, we'll say, so villages, social networks like villages or high schools, and they're doing an intervention of some sort of abstract form where they're trying to intervene on individuals sort of behaviorally and trying to move the needle on a network level outcome, a village level outcome. So this is a photo from a research project led out of the Yale Human Nature Lab, field work in Honduras, where they're going in and distributing multivitamins to villagers in these rural villages in the hills, and then going back, mapping out the social networks and looking to see how can we introduce interventions, multivitamins, also water purification tablets, and maximize the adoption of this product at the village level. So in this sample social network, it's sort of a directed graph. We have these questions of sort of, would it be better to seed this intervention at the two red individuals, the two blue individuals, or maybe the two green individuals? They have different advantages. The red nodes are sort of more central. The green nodes are tightly connected. So there's sort of advantages and disadvantages to sets of different ways to compose these sets and sets of different size. Most broadly, sort of different seed sets map to different network level outcomes. So there's been a number of these types of interventions lately. There's the large one run in Honduras across 32 villages. There's an even larger intervention run with farmers weather insurance in villages in China. And there they were trying to train people or educate people on the advantages of insurance products and looking at the fraction of households that adopted at the village level. As a third example that sort of establishes the generality of the problem, there's this study out of the country of New Jersey, sort of the state of New Jersey, where they looked at 56 middle schools, and they were evaluating anti-bullying programs. So they were going in, selecting a set of students, and putting them in an intensive intervention to sort of training them on anti-bullying best practices in social psychology. And then they were monitoring the peer conflict events that appeared in administrative records over the course of the academic year. So these are all examples, and the figures at the left are sort of networks from these different contexts: the Honduras villages, the Chinese villages, and the high schools in New Jersey, which are larger and have more subtle social structure. So I really want to sort of establish the significance of the question here, because here's one of these titles that's a question mark, that's a working paper. Can network theory-based targeting increase technology adoption? Here it's the research context is 200 villages in Malawi. This is sort of a hot topic across many contexts about how can we go into networks and maximize adoption via how we intervene. Now, for the computer science audience, there's a relatively a modern classic problem here, which is sometimes called influence maximization. This is work by Kempe, Kleinberg, and Tardush, which, given a graph and an influence model, the goal is to select seeds to maximize total adoption. It's a combinatorial optimization problem. It's typically regarded as NP hard, but approximable. That's sort of the celebrated result in the influence maximization results. Now, the issue with influence maximization is that there's different results for different models. So it's really a model-based optimization. So what I'm talking about today is this model agnostic framing of evaluation, where you're looking at these interventions that went in and asking how could different ways to sort of seed the network lead to village level outcomes. It's more of a statistical problem rather than an optimization problem. You could use this statistical framework to evaluate targeting algorithms. And that's sort of what we're going to do narrowly, just looking at simple pairs of simple algorithms rather than sophisticated algorithms. So the two seeding strategies where I'm going to compare is sort of this idea of comparing random targeting and this other targeting strategy that's kind of all the rage in this literature, which is what's called one-hop targeting or nomination targeting, where instead of targeting random people, you target, you pick a random person and then select a random friend of theirs. Now, this leverages what's known as the friendship paradox to effectively land at higher degree people. Your sampling individual is roughly speaking, proportional to the number of in edges they have. And so you're more likely to land at high degree people, who are then sort of by a reasonable social theory are going to have more influence in their network. There are several of these studies that have been done to try and evaluate one-hop targeting versus random targeting. But what we show in this work is that you don't actually need to be asking the specific question of random targeting versus one-hop targeting, because random targeting actually contains one-hop targeting as a special case if you reweight the data. So what do I mean by that? I mean that when you look at the different sets that you can select with one-hop targeting, when you're doing random targeting, you're getting any sort of set of size 2 uniformly at random. But every time you get a set, that set has a probability under one-hop selection. So by the friendship paradox is more likely to select central nodes, and that's sort of its non-uniformity across the space of sets. But importantly, you can use random targeting data to evaluate how well would you do if you had done some sort of more intelligent sort of selection process. And this is broadly the trick of off-policy evaluation that's had a lot of influence in the last 5 to 10 years in online recommender system design. So this is a sort of web technology paper that's prominent in the literature, where it was a Yahoo Labs project where they showed random articles on the front page of Yahoo News for a period of 1 week, and then use that data to evaluate other policies. So essentially, when researchers have been going in and using random targeting, we can use that to evaluate other targeting strategies using these same ideas to try and improve these interventions in development economics. There's a sort of a math take on this that I'm going to skip, but the main finding here is that when we've gone in and reanalyzed these random targeting approaches, we have found that it turns out that one-hop targeting is not doing better. There's sort of, if you look at the estimate here, and there's a bunch of error bars here because I have statistics collaborators here, error bars computed several different ways. We find that one-hop targeting leads to less, as a targeting strategy, is expected to lead to less adoption than random targeting. The same thing when we look at the anti-bullying intervention, one-hop targeting would lead to more conflict, would lead to a smaller reduction in conflict in the high school data. And this really goes against a lot of the theory that says that these one-hop targeting ideas are really, really good. So The high level point here is that interventions on networks are really complicated. We're doing interventions on networks because we're trying to activate non-trivial network effects, but network effects are really hard to intuit around. And the evidence from this initial evaluation shows that in weather insurance and anti-bullying contexts, one-hop is no better or possibly worse than random targeting. And this is work that's this last week sort of finally came into print in Management Science, and it's really a doorway into a lot of other off-policy questions in network evaluation that I've been thinking about. So thank you.
Thank you, Johan, for sharing this fascinating area of research. Now we have about 10 minutes for Q&A. If you have questions for our panelists, please post your question on the Expo Slack channel. I haven't seen any questions from the audience yet, so let me get started by asking a couple of questions. My first question is for you, Ashish. Ashish, what are the likely future scenarios for cryptocurrencies, and how will cryptocurrencies change the way we do business?
So I feel, that's a big question. First, thanks for inviting me. I must clarify that my understanding of cryptocurrencies is based largely on algorithms and market-based thinking and not on actual systems level implementations. But I feel like there are two aspects to currencies like Bitcoin. One is the underlying blockchain technology. And that I feel is going to find massive use in things like cryptocurrencies which are run by banks or by states, or just in cryptographic assets which are not currencies. Could be, for example, data exchanges, or could be non-fungible tokens. And so this blockchain technology, I feel like, is here to stay. Systems like Unisop, which exchanges cryptocurrency assets, are also likely here to stay. I feel like the future is sort of away from specific currencies like Bitcoin, distributed currencies like Bitcoin, and more towards currencies which look like more centralized currencies, script systems. And I feel if distributed currencies do come about, they're likely to come about as a result of some trusted interaction. So for example, there's a layer on top of Bitcoin called Lightning, which allows people to establish side channels for payments, which are pairwise side channels for payments. And they're based on sort of either trust or collateral. So I feel like currencies will ultimately either be based on collateral or trust, or some kind of legal backing by a government or a bank.
All right. The next question is from the audience for you, Johan. You talked about some networks like school bullying example that seem much smaller than the web scale effects, often evaluated with off-policy methods. But how do you adapt these methods to deal with smaller data sets?
Yeah, that's a great question that highlights one of the reasons why it's been really important to bring sort of advanced tooling and advanced math to this problem. So one of the perspectives that motivates the current work that I was talking about here is the fact that in these village contexts, in these school contexts, the villages and the networks themselves are small, but we actually have a population of networks. We have 30 networks, we have 200 networks. And there's been a line of work that's been looking at these intervention questions by running randomized controlled trials where they make they make treatment assignments at the network level. So they take out of 30 villages, they take 10 of them and they do one thing, they take 10 of them and do another thing, and another 10 and do a third thing, and then evaluate the different intervention styles. So that's in the sense of the types of analyses that are feasible there, this is very, very small data. This is similar to the medical trials where you have sort of 6 patients in every arm. And so it's really important to have sort of as efficient error bars as possible when you're trying to evaluate the different, compare and contrast the different policies there. And so that's why what we're doing when we're doing off-policy evaluation is we're able to sort of get more juice out of the fruit by looking at the random seeding and saying, well, yes, those are representative of random seeding, but we can actually also reweight them to evaluate other policies. And so it's actually like this, in an ideal world, we would have enormous population of hundreds of networks, but actually here, every village is a research assistant spending a month in a village. It's sort of a bizarre amount of shoe leather work to gather each of these village data sets. And so it's really, we're using off-policy evaluation to squeeze more value out of every sort of village level data point. And also the fact that we're looking across networks gives us sort of a lot of statistical power. That's a harder analysis to do on the single large sort of marketplace networks that a lot of off-policy ideas are used in. But yeah, so it's really about the value of sort of like cranking up your methods when you're dealing with only small data.
Thank you, Johan. My next question is for you, Ashish. How can we as individuals and as a civic society have a role in governing and regulating immensely complex pieces of technology like, say, blockchains or AI algorithms?
Thank you. So there's a group of us at Stanford who's been wrestling with this question and a very specific form of this question. In fact, much more narrowly scoped, which is how do we determine that some of these large media companies such as Google, Facebook, and Twitter are doing a good job of policing falsehoods while also encouraging free speech? And how do we know that the targeting methods that they use or the ranking methods that they use sort of reflect the values of the consumer who's actually consuming this media? And we are focused primarily on political speech. And what we have found is that there's a space here for a regulatory middleware, for some kind of a middleware based approach. These corporations and their algorithms are so sophisticated that it's hard for an individual to have an opinion about whether they're doing a good job or not. But you can imagine a big consortium, for example, one formed by Stanford University and a couple of other universities, one formed by the ACLU, one formed by Fox News, and a third entity. And these could essentially act as a middleware layer, and they would be the ones who would sit between the platform and a consumer and try to exercise editorial discretion on the part of the consumer. They're also the ones who will audit whether these platforms are doing ranking, which is consistent with what the consumer wants. So I feel like this approach of having this middleware, which equals or nearly equals these big tech platforms in algorithmic and machine learning sophistication, but whose business model is not aligned in any way with these large platforms. And the goal of this regulatory middleware is to be entirely transparent in what it does and to sort of export the values that it promotes in simple consumable chunks. And then the task of a consumer or an individual then becomes to sort of, or us as a civic society, becomes to establish a regulatory frame and provide the funding for this middleware layer to exist, right? To provide sort of adequate supervision of this middleware, and then assume that this sophisticated middleware will be the one that will take over this regulatory response, this auditing and policing of the tech platform ecosystem.
Thank you, Ashish. I know there's a couple of more questions for you, Johan, but we are running out of time here. So what we'll do is we'll just pass along those questions to you, Johan, and we'll write back to the audience members with your answers. So with that, we come to the end of our society-centered session. Thanks to Susan, Ashish, and Johan for their wonderful presentations and also for answering these questions. We will now take a 10-minute break.